Let's take a look at practice question set 2B now. Practice question set 2B talks about this ski race. Starting gate of a downhill ski race, the skier pushes with his arms and legs, to get as fast as possible of a start. The skier leaves the starting gate with an initial speed of 1.6 meters per second. This is misleading the way they describe this, right? An initial speed of 1.6 meters per second. Look, when you're talking about going down the hill, that's the initial speed, right? But you're going to see in a moment, the question says, what's the magnitude of the impulse on the skier as he leaves the starting gate? I don't know what just happened there. As he leaves the starting gate, well, that speed that we just saw there, that 1.6 meters per second, is actually the final speed if I'm leaving the starting gate, right? What's his initial speed in the starting gate? 0. He's standing there, right? Ready to go. So even though they say it's initial speed, it is for the next problem, the trip down the hill, but it's the final speed for question number 1. Race course is made up of both steep and flat sections. At the end of the first flat section, there's the distance. He's going at 20 meters per second, so he's sped up quite a bit. And then at the end of the next steepest section, he's going at 33.3 meters per second. What's the impulse as he leaves the starting gate? Let's say delta P is equal to M times delta V. His mass is 68.2 kilograms. And his change in velocity is, well, VF minus VI, right? His final velocity is 1.6. His initial velocity is 0. And I can't remember what we get when we multiply those. I'm going to say maybe B. Is that right? Is it A? 1.09 times 10 to the 2 Newton seconds. Good? See why we use the 1.6 minus 0 there? Anybody try using the 20 or the 33 in there? Yeah? Initially, yeah. That would not be an uncommon mistake. Okay? And, I mean, they're doing that for a reason, right? They're doing that to try to trick us. Don't get thrown off by that word initial speed. Okay? This absolutely can be the initial speed, but of a different problem, not of question number 1. Okay, next one says, a full draw is the maximum distance that an archer can pull back an arrow. Using the recurve bow shown below, a particular archer requires an average force of 130 newtons to pull a full draw of 70 centimeters. What's the question? When the archer releases the arrow from full draw, the magnitude of the impulse that the bow gives to the arrow is what? Impulse is equal to F times delta T equals M times delta V. What do you want to do here? It's a tricky question, eh? Tricky one. Anybody get this? Yeah? What'd you do, Kara? Sorry? Oh, we used F is equal to M times A. Okay. So we use F is equal to M times A. Listen, this stuff that you learn in Physics 20 is not out of the question now, right? You're allowed to go back to that. So Kira said the force was, what was the force? Actually, let's do it on this page so we see the, so we see all the data there. So the force was 130. And well, we had the mass, right, of 20.6 grams. So we could find the acceleration. Is that what we did? A is equal to F over M. A is equal to 130 divided by 0.0206 grams. Really, we should have circled that because it was grams. What'd you end up getting for acceleration there, Kira? That's okay. I know sometimes you just kind of keep your numbers in your calculator. And so I'll find that here. 130 divided by 0.0206 gives me 6,310.679.6. So there's my acceleration, right? Then what? Anybody else want to jump in here now? Okay. Okay. VF squared is equal to VI squared plus 2AD. VI would presumably be 0, right? VF would be the square root of 2 times 6310.6796 times the displacement of 70 centimeters, 0.7. Kenny, do you have the number there for VF? Okay, I think that might have been the impulse here. But, so 2 times, I'll do this here. 2 times 6300 times 0.7. Let's square root that. 93.99. And now what? Probably this, right? 0.0206 times a change in velocity of 93.99 minus 0. Right, final minus initial velocity. Is that what you did? Times it by 0.0206. 1.94. That's a tough question. Yeah, that's a tough question for sure. Yep. Oh, okay. Okay. Interesting. I never thought of that one actually. So, Mark, you said D is equal to VIT. Okay. So you got this. You got this is 0. You got. Oh, you don't have acceleration though. Oh, okay. 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 So you did this, like Kira did, and then found the acceleration. Instead of plugging it into VF squared, you plugged it into this to solve for time, and then said F times T instead of M times delta V. Okay, I'm going to go out on a limb here and say you got the same answer. And you should, absolutely, right? In the end, is this a valid equation when something accelerates? Yes. Is this a valid equation when something accelerates? Yes. If you're going to use a valid equation, and assuming you do it correctly, you use it correctly, you got to get the same answer as somebody else, even if they used a different valid equation, right? You can't use two valid things and get two different answers. It can't happen. So don't worry about, somebody else, oh, he did it this way. That's okay. It doesn't matter. If you're doing it a valid way, it doesn't matter if you're doing it the same way as somebody else or not. It's gotta work out to be the same. Okay, good there? All right, next question. I think this is the last one, wasn't it? Just 3. A rock climber falls and is saved from injuries by a climbing rope that is slightly elastic. The importance of the elasticity of the climbing rope can be understood in terms of the impulse because elasticity results in, well, we know what this is before we even look at the options, right? We want the rope to be elastic because we want to, when the person stops, we want to increase the stopping time to decrease the force. So what is it, A or C here? Decreased force in an increased time interval, the answer would be A.